Hi, my name is Karen Jennings. I'm going to talk today about using carbon dioxide as a refrigerant. I want to describe carbon dioxide as a feasible, appropriate gas that is cost-effective and environmentally friendly medium for the transfer of heat. I'm going to explain the government regulations requiring the phase-out of hydrofluorocarbons. I'm going to define the refrigeration cycle and explain some of the gas properties required for a refrigerant. And then I'll finish with the effects of current and past refrigerants. The purpose for choosing this is because it's a tangent to the work that I currently do. And I'd like to understand some of the processes that are used in deciding the next generation of our products. To prove CO2 is a good alternate to hydrofluorocarbons. It has an environmental advantage. It's non-toxic, non-flammable, and it's not regulated by the government. And it meets all the properties it needs for the purpose of heat transfer. When I talk about applying to the product that I use, I'm going to talk about transport refrigeration, and it refers to items like this. This is a refrigerator that goes on a tractor trailer on the semis that you see going down the highway. One of the purposes of looking for a new refrigerant is there's a threat to the ozone layer by the use of hydrofluorocarbons. They contain chlorine and fluorine, which are dangerous and obviously affect the ozone layer. And in 1987, Ronald Reagan signed the Montreal Protocol, which will phase out greenhouse gases by the year 2020. Carbon dioxide isn't on this list, and the refrigerants that we use today in your car or in your house are R22 and R134A, and some of the other machinery uses ammonia, and we'll compare some of those. The definition of refrigeration is the process of removing heat from one place to where it is not wanted and transferring to a place where it makes little or no difference. So in the transport refrigeration business, that means taking the heat from the box, which is the inside of the tractor trailer, and moving it to the outside air. And a common misconception for cooling is that the air is cooled, but is really the heat is removed, the air isn't cooled. To define the refrigeration cycle, it's based on the temperature-pressure relationship of the gas. It'll change the state from a liquid to a gas and vice versa, and that's where all the heat exchange occurs. So the more heat required for a refrigerant to change state, the more heat will be removed. So how does this work? You need four components mainly in the refrigeration cycle. You have the evaporator, which is similar to the coil that's inside of your house. It changes from a liquid, it absorbs heat and changes the refrigerant from a liquid to a gas. The next, it goes to a compressor where it's turned into a high pressure hot gas. This flows into the condenser. The compressor allows the condenser to suck in the gas, and it'll flow out of there as liquid gas mixture. And you also need, the fourth component is a metering device, and that lowers the pressure so that the refrigerant forced back to a liquid, and then it can restart the cycle. Some of the properties needed for a refrigerant is the boiling point and the saturation point has a lot to do with its ability to absorb and give out heat. The refrigerant must be safe, it must be detectable, it must have a good boiling temperature, and it must be recoverable. It means you can measure it, and you can also claim it or reuse it. We want to compare some of these points with another refrigerant. Let's use ammonia. Ammonia is a high health hazard. It's corrosive to the skin and eyes and lungs, and it's an immediate danger to life. It's flammable at a 15% volume in the air, and it can explode. And one of the good things about ammonia is it has a low odor tolerance, which means it's really smelly, and people avoid it. This is obviously not a good choice for a refrigerant, even though the boiling point is -33, which is a good range. If we compare that to carbon dioxide, it has few health hazards. It's low toxicity, it's non-flammable, and it has no odor. The higher boiling point requires a high pressure system. I find this better than ammonia. Some of the pros and cons. The cons are carbon dioxide has a higher pressure, so it's harder to service. And the higher quantity, if a concentrated quantity is in contact with a person, then it's unhealthy. Some of the pros are carbon dioxide doesn't contain chlorine or fluorine, so it's not one of the regulated gases that will be phased out. It can be sourced from other processes as a byproduct of the sugar industry and some other industries, so it can use up waste from other processes. And it also exists in nature. It's not harmful to the existing environment. And even though the high pressure might be a little harder to work on, it allows the miniaturization of components, so the tubing and compressor size can be smaller and be more cost effective. In summary, I find that carbon dioxide is an adequate substitute for R22 and R134A, and definitely better than ammonia. It's not regulated, it doesn't expire, it consumes processed waste, and it's within the acceptable ranges of chemical properties and has lower safety concerns. I recommend this to my company to research the possibility of using carbon dioxide in their application. I thank you for watching my video.